Okay, continuing on with our world data storage system. In this video, Nelson is going to be getting in place the record info, the record header, and a tuple utility class that we can use.
Alrighty. The first step is actually, I failed to mention this where we should have originally, but this world data storage.library is actually going to be a .NET 3.5 project. And the reason is a .NET 4 project won't load on the version of Mono that Unity uses.
Okay.
So I'm going to yank that back, hit yes, and then just for whatever, rerun this. And we get a failure to build, which is awesome. First of all, we do not need references in Microsoft.C#. That contains the dynamic features, or the runtime code for the dynamic feature.
Mm-hmm.
And then we have this. So it looks like there was another breaking change in the between .NET 4 and .NET 3.5. It looks like the binary reader and binary writer are implementing iDisposable explicitly instead of implicitly, which means we have two options. We can either do iDisposable reader dispose like that, or we can go ahead and do reader.close, which does the same thing, and writer.close, which also does the same thing. So now we get a successful build, and if we run our tests again, we should get green. Okay, so the first thing is I'm going to go ahead and write a little tuple class because I really like tuples, and I'm probably on any Unity project that we work on, I'm probably going to be taking this class around because I use them quite often. Have we ever gone over tuples?
No, I don't think we have. So if you want to take a second and explain it to people that have never seen one.
Well, I can go ahead and break out into the console because the console is a .NET 4 app, and we can actually use the built-in tuple class, which is part of .NET 4. So a tuple is an interesting thing. Basically, actually, this is I'm not going to use implicit typing just to make it very clear what's going on. Basically, what a tuple is it's an immutable data structure of ordered arbitrary data. And what I mean by that is that the data structure itself will never change. You cannot edit any items within the tuple. The items are ordered, meaning you can access an item by the 0 index 1, 2, 3, or 4. But the size can never increase or decrease of how many items are in a tuple. And further, the types between those items can change. So if you want to compare a tuple to, for example, an IEnumerable, a tuple has a fixed amount of items that have arbitrary types that never change. An IEnumerable has many items that all are forced to have the same type. So does that make sense? The way the tuple classes are implemented, and I don't know how, let's just do that. The way the tuple classes are implemented in the .NET is there's actually multiple ones. There are the so for example, this is the two-item tuple, and we're not going to be implementing the equals or compare to, so you can ignore all this stuff. That's not important. What's important is the first bit, and the first bit is we have two objects, item 1 and item 2, and here, Jason.
Yeah, I see that.
This is .NET 4 too.
No, I know that. It's funny.
Anyway, so we have this. This is a two-item tuple, and it has two items because it's a two-item tuple, and they're generic, so they can be anything that you need them to be. And then it contains those two items, and as an item 1 and as an item 2, they're completely read-only and immutable, and you can only set them during construction. So actually, this code actually should, just to make things more clear, that's how it would be written. Let's say we want a tuple of a string to an int to a float. So see, the first item is a string, next item is an int, third item is a float. And then so now we can do tuple.item1 or tuple2.item1 through 3. You can also do something with the really big tuple type, which is going to be this one. If you have 7 or more than 8 items, you can go, like for example, int, and then you could put another tuple in, and there. So now we have a T1, and he has a rest item, which we can go in to get the final item. So basically, we can make tuples of any size. We're only going to be implementing a 2-item tuple because that's all we need for the code that I'm writing. So yeah, the final thing to know is that in this case right here, this is completely redundant. Well, I mean, obviously I'm using implicit typing, but or not using implicit typing, but this can be created implicitly. Unfortunately, constructor arguments cannot imply their generic arguments, but they did create another class, a static tuple class that has this create method. And using generic type inference, it's able to not have to repeat the same type arguments on both sides. This actually translates into string, int, float. All of these are inferred because all of these items matched on those particular types.
Right. Cool.
And then finally, why would you ever want to use a tuple? If you ever have been coding and you needed 2 return values, there's a reason to use a tuple. Or 2 or more return values or something. Or if you're writing code and you need to associate an integer with a string, but you don't want to go out and make a structure because that would be pointless, then you would use a tuple. So yeah, the implementation is going to be very straightforward. I'm going to go ahead and make this internal, because generally in an object or in a functional language, using tuples publicly isn't an issue. In an object-oriented language, people might get frustrated because tuples really don't communicate intent very well when you bring them out of context. So I generally will only use tuples for private stuff, for implementation details and so on, because like I said, once the tuples kind of leak out of the private context, they start to lose their meaning because obviously they don't have no names. So I'm going to go ahead and have T1, T2, and then I'm going to have a public T1 item 1 get private set. I'm going to use a getter and a private setter. This isn't the same thing that the .NET framework used, but it accomplishes the same thing. Okay, so if you want to look at that. Then finally, I'm going to implement, how did that? My internal static class tuple with a public tuple T1, T2, create, T1, T2, T1, item 1, T2, item 2, and it needs to be static. And then I'm going to return out a new tuple of T1, T2 with item 1, item 2.
Cool.
So yeah, does that make that's all
Absolutely.
straightforward? Okay, so the next thing, I guess, is the record info class. And the record info class is just going to be something that I use to talk about records outside of the context of a database. So there will be some methods in the database in the future that can actually ask information about records, or, for example, ask which records are corrupted or not. So to be able to represent a record outside of this project, I'm going to create this record info class. And basically, he's just going to go ahead, and I don't know how to spell coordinates. It's embarrassing. He's going to go ahead and contain basically the personally identifiable information of each record. And then I'm just going to go ahead and generate a constructor. So wait for that to refresh on the screen. And so this is just a class with 3 things in it. And these 3 things are what are used to identify particular records.
Right. Yeah, the exact same thing that was demonstrated on the Photoshop whiteboard at the very beginning.
Yeah. All right. So the last thing is going to be the record header. And we already talked. How much should we talk about the record header?
Just a little bit in the discussion with the graphic, talking about getting from record to record, knowing as far as how far over we need to go for the next record, and the linkage.
So the record header is going to be obviously at the beginning of every record, and it's going to have a bunch of information. We're going to have and everything's going to be public and immutable and ugly and gross. But this is going to be an internal class, so it's okay. Header size, we need to know how big the header is. We need to know where the next record is. We need to know the coordinates of the record. We don't actually need to know the coordinates of the record for strict usage, but it'll come in handy once we need to, for example, know which records are corrupt or not. The record needs to know its type, or the record header needs to know its type. Needs to know its layer, and it needs to know its version, and it needs to know its data size. This is the how big is the data of this record, and then finally we need a checksum. And I'm going to go ahead and implement two constructors, one that's blank, and the other one that's going to take in a binary reader and a header position. Okay?
Mm-hmm.
So then I'm going to basically just read in all of this data again. So I'm going to basically be retyping out everything that I just typed out. So this is fun. Read int 16. Oh yeah, header size is up short. And what is this guy? This guy's a long, so we're repeating an int64. Our coordinates are actually going to be interesting because this is a structure. So all I'm going to do is create a new vector2 and then do br. Okay, Jason.
Yes.
Without looking at the documentation, how do you read in a float from a binary reader? What method do you use?
Right offhand, yeah, I'd have to go to documentation. That's something I haven't done in quite some time.
But you would assume that read float would be good, right?
Well, that
would be a good name.
Yeah, that'd be the first thing that I'd be looking for.
Yeah. How long would it take for you to guess read single is the correct method for this?
Interesting.
It does make sense because it's a single, or if it doubles a double, a float's a single, I guess.
Yeah.
But it's still like, come on. So we have to read singles in. Our type is going to be a bit interesting because we're going to be using the type, which is in system namespace, and we're going to use the getType method, and we're going to have to decode this stuff. This is going to be kind of funny to explain. I'm just going to break it out. I don't want to do that. Okay, so that's basically what we're doing. We're reading in the string size of the type name, right?
Mm-hmm.
Then we're reading in the bytes based off of what the number was, and then we're decoding it, and then we're passing it to the getType method.
Okay.
So I just want to, before I go ahead and inline everything again, because it might look a little funky. So that's what's going on here. So this is a step, that's a step, that's a step, and so on.
Cool.
And then our layer is going to be read int 16. And our version is going to be read int 16. And our data size is going to be read int 32, or not. Why? Hold on. Data size is read int 32. Oh, read, yeah.
You went.
I'm dumb. Ignore me. Then checksum is actually going to be the same thing. I'm going to do something fun here. There we go.
Nice.
Okay. So if you can see, I made this method appear out of thin air. That just takes all that cruft and moves it away. So I don't have to duplicate it between checksum and type.
Very nice.
So finally, we need a, and I didn't actually fill out header position for some reason, because header position isn't read in 32, it's header position that gets passed in by who's ever loading it. And yeah, so that's the loading of the header. I'm going to go ahead and make sure that I'm getting, because if I get any of these bytes wrong, then stuff's going to blow up. So header position or header size is an N16 short, N64 long, vector 2, type short uint string. So that should be fine. Now we need to write a method for writing, and my cursor just flew across the string and started deleting things that shouldn't have. So now we have a void method write, which, if you could possibly guess, is just going to write the stuff back out. Unfortunately, this is going to require, the first thing that we put in is the header size, which is going to require that we pre-calculate all of this stuff. Right?
Absolutely.
We need to know how much, obviously how big everything is, and the type, for example, which we're going to serialize into a string, and this string on the checksum, they're inconsistent because they're obviously strings. And instead of, what we could do is we could use the writer dot write and then the string overload. The problem with that is that the way that that writes out strings, it's documented. I read about it. It uses 16-bit width or 16-byte characters for whatever reason. But I don't want to do that. I want to go ahead and encode it myself and then know exactly how many bytes it's going to be using. So to do that, the first thing I have to do is get the type bytes, which is going to be encoding UTF-8 get bytes from type.assembly qualified name. And then now we need the checksum bytes, encoding UTF-8 get bytes, and then checksum. So now we're doing our own encoding, and we know how big those are going to be. Excuse me. So now we have writer write. The first thing we need to write is the header size. This is going to be annoying, actually, because I don't want to go ahead and just pre-calculate this out all myself. I want to do it field by field, so if we ever add or remove fields, we can do that easily. So let's just go ahead and do size of short plus size of long plus size of float. Well, we can just go ahead and multiply that by 2 for a record, for vector. And now we do the type, which is going to be a size of int, right? Then it's, because that's going to be how many bytes there are, and I'll show you that in a second. Then it's going to be type bytes.length plus size of short for the layer plus size of short for version plus size of uint for the data size. And then we need a size of int for the checksum's character count or byte length, and then checksum bytes dot length. And I screwed something up.
You're missing a plus.
Yes. Oh. Why did it think that was appropriate to do?
Wow.
I
At a loss for words.
Okay. There. Okay, so now we actually have to go out and write all these things. It's a lot of manual labor, I know, but I didn't want to really break things out too much into cool little abstractions and serialization libraries and all that stuff, because I wanted this in particular to be as quick as possible.
Right.
So that's why there's a lot of grunt work here. So we're going to write next record first, because we've already written the length. Actually, just to make this more explicit, we go ahead and do that, and then I'm going to go ahead and slap Visual Studio some, or ReSharper, whoever's responsible for this.
My guess is going to be ReSharper.
Okay, so now we have a header length. Our next record. Now we need our coordinates .x and our coordinates .y and our type bytes .length and then our type bytes. Actually, don't like that name. I'm going to call them type name bytes. That makes more sense. Because it's not the actual bytes of the type, it's the bytes of the name of the type. And then after the type name bytes, we need our layer, and then our version, and then our data size, and then our checksum bytes length, and then our checksum bytes. And that's that, I guess.
Cool.
So, yeah, is everything here pretty straightforward?
Yeah, absolutely. So, I mean, is there anything else that you wanted to discuss, or?
Well, that's about it.
Yeah.
As far as record info, record header, tuples, and tuples, we got all these classes figured out.
Yep. Okay, well then let's just go ahead and wrap it here, and we'll catch everybody over in the next video. Thanks a lot, guys.